Hey everyone, welcome to my channel. If you are interested in speaker design and improving sound quality, subscribe and join us. In this video, we're going to speak about the other known horns. Before diving into explanations of the said horn, it is logical to find a good reason for the sound amplification of horns. This is an electrical equivalent of a speaker. As you can see, it includes a transformer, a gyrator, electrical elements, and mechanical elements. On the secondary side of this transformer, if we have a low acoustic load like air, the acoustic voltage or the sound pressure level will be low. If we put a high acoustic load on the secondary side, the acoustic voltage will be higher, so the sound pressure level will be higher, which means the sound has been amplified. This graph indeed shows the amplification range of the horn, and, as we said, the flatter the graph, the more constant the impedance value of the horn, or a constant bigger load for the speaker. It is so important to know these parameters and import them to acoustic software to get exact results. You can watch these videos to learn how to import them into software and find out what they are. If you want more explanation, leave in the comments below for me. Even if you don't know about elementary parts like resistors, inductors, and capacitors, feel free and tell me to make a video about them. Spherical wave horns. It was invented in the late 40s by Klangfilm. We've definitely seen these beautiful waves in nature. They are started from a point. The more they move forward, the bigger the circle. All the points on the circle have the same power, and they reach a destination at the same time. Since the sound waves travel throughout the horns, this explanation will be true for them. If we consider plane wave throughout the horns, the problem is the displacement on the horn walls will not be equal to the central axis. But if we consider the waves as spherical caps, the problem will be solved. The assumption is that the horn expands with the constant radius on a horizontal line, something like this. This is also the shape of its wavefronts. So the folded ones are usually spherical wave horns, but it is possible to cut the horn before its fold. Rho is the constant radius of the wavefronts, and as you've seen, the horn was shaped according to that. Yo is the driver radius, and Ho, or the height of the wavefront at the throat where the speaker is mounted on the horn, is calculated by a simple formula. We don't need to keep these formulas in our mind, but for better importing into Excel, we should know what the parameters are. M is the growing factor and is given as. In the next steps, Ho has been grown and the new value is. S is the area of these spherical cap shapes or the area of the wavefront. Y is the changing radius of the horn mouth in every step. X, H, and X are illustrated as well in the figure. If we select the cutoff frequency of 350 Hz, the result will be. Now, if we import these formulas into Excel, the side view of the horn will be made. Watch this video series and do it from 0 to 100 to master it. All the steps of spherical wave horn design have been completely explained according to the current video. It seems the horns on the old gramophones are a Tractrix curve shape. Today, we owe this great horn to the efforts of Paul Voigt and Dr. Bruce Edgar. In this horn, like spherical ones, the side view is formed by moving the fixed radius, Rm, on a horizontal line, but its flaring speed is lower than a spherical horn, and it cannot fold on itself. Rm is often obtained by this formula. Fc is the cutoff frequency in all the said formulas. Note that X is the distance from the mouth, not the throat, and the resulting side view in Excel will be in reverse. Rx is the mouth radius in every step. Implementing these formulas in Excel is very easy. As you can see, we've implemented all parts of these formulas. Define Rx at the first step as the throat radius or the driver radius. As you can see, X or distance from the mouth is the maximum, and the Excel file works correctly because the maximum distance based on the said explanation is the distance between the throat and the mouth. ln is the logarithm function in Excel. If Excel is not familiar to you, write in the comments below. I would be happy if I can make a tutorial to help you. In the end, on the Insert tab, you can generate this graph by selecting these two columns as the graph entries, and the Tractrix shape will be generated. You can make your horn by importing the Excel points into any simulation software. Then try to make it with your desired material. As you can see, a horn designer first creates these stair shapes based on the defined points in software programs like Excel. The next step is to remove the stairs and rough surfaces. Oblate waveguides, a new age horn that provides good directivity control for high-frequency drivers. The cutoff frequency is not defined, since its coverage angle is the key to getting its side view. Formulas are simple, and it will also be easy to import them into Excel. This horn is a modified conical horn. Note that its original shape doesn't include the fold. Watch the tutorials in the section related to the Oblate waveguides. Now, it is time to compare the result of the said horns. This is the side view of a 75 Hz spherical horn. The red one is Tractrix with the same cutoff frequency, and the green is exponential. Exponential has the slowest flaring rate, and the spherical is the fastest. All these horns are usable. They can provide a good sound quality and a flat impedance response. Design your horns and compare the results. Good luck!